Okay, so here is our follow-up video clarifying what we're doing in classwork 17, including that challenging solving the mystery of the mean regarding confidence intervals. So I'm going to go ahead and review the questions on the first page first, just to make sure everybody got those concepts okay. And I'm going to do it a little backwards. I'm going to start with 3 and 4, and then I'm going to go back to 1 and 2. So with 3 and 4, I asked you to look at these slides about, comparing, we want to know what's the difference between critical t and sample t, and then how does that apply to alpha versus p-value? Because it's really confusing. We have two different t values, and then what's the difference between this 0.05 and this p-value? So I like to use this analogy of a baseball diamond. And you can think of other sports as well. Basically, any sport where there's a foul line, right, is going to work for us here. So, oops, that's not what I want. Okay, so what's the difference between our critical t and our sample t? So the critical t, this is really our foul line. So this is a set boundary that is going to basically help us make a judgment about whether something is in or out. And so this comparison, critical t versus sample t, let me just make a little note here that this is what we use if we're really, I would say, if we're doing a t-test by hand. This is the easy way, is what we end up doing is we compare our sample t and our critical t. So we need to understand, how does that work? But this is really more relevant if we're doing our t-test by hand, where we're actually working out the calculation and we end up with a calculation where we have a t-value and we need something to compare it to know, okay, well, what does that mean? Is it significant or not significant? Then we'll go ahead and we'll extend our analogy to comparing alpha versus p-value. And this is really going to be relevant for us when we're doing a t-test using the computer. Okay, so most of the time in practice, as I've said before in this class, we're doing things on the computer. In practice, in real life, in research, in your other classes, in graduate school, if you become a researcher, if you're a statistician, statisticians don't sit around doing all their problems by hand. That would be ridiculous. Why would you take, 5, 10 times as long to do a problem and make it a lot more probable that you're going to make a mistake because we're humans. We make lots of mistakes. That's part of being human. So in practice, this is going to be what we're doing. We're really going to be comparing, okay, I have an alpha value and a p-value. So in this class, we're going to be switching to doing we do a lot of stuff using JASP. As I've said before, there are lots of different statistical software packages. JASP is just one of them. I choose JASP for this class, even with all the problems that we experience with it, with people not being able to download it or get it working. The reason why we use JASP in this class is because it's free and you can use it on the web. Theoretically, if you can get it working, you're supposed to be able to use it just in a web browser without downloading any software. And that's why I like JASP. It also gives us our output in a format that is ready to use. It's already in what we call APA style, APA standing for American Psychological Association. It's the style that not only psychologists, but a lot of social science researchers, a lot of education, a lot of different areas tend to use this style when they're writing reports, when they're writing up journal articles. And so that's why I personally like JASP. It's free. Hooray. It's available widely. You can use it in a web browser. And it's once you get the hang of it, it's fairly easy to use and it gives you your output in a way that you don't have to go back and edit a bunch of stuff like you would with other software systems. Other software systems you're likely to hear about a lot. One of them in particular, you may encounter this in other classes, is called SPSS. And I know we're going on a little tangent here, sorry. But again, I know people are still contacting me, letting me know I'm having trouble with JASP. What do I do? Don't stress about it because, like I said, JASP is just one of many different software systems. One of the other most common ones used in psychology and social sciences is SPSS, the Statistical Package for Social Sciences, is what it stands for. And the reason why I used to use SPSS in my classes, and it's actually what I was trained on in all of my classes, the reason I don't use it, it's very expensive. If if I wanted each of you to have a license for SPSS, you would have to shell out $50 each, and that's the special student rate. If you're not a student, if you're a working professional, it's like $5,000 for a 1 year or 2 year license for SPSS. So that's why I've stopped using SPSS because it's really expensive. And the output that it gives you have to go back and edit a bunch of stuff to make it in APA style. So just so you're aware, you may see this SPSS come up a lot with regards to statistics related stuff. And it's great, it's very powerful, you can do all sorts of stuff with it. It's really expensive. That's why I don't use it. So again, this number 4 is going to be important for us for the reason that it relates to what we do when we use a computer, which is most of the time, almost all of the time in practice. Why we start out with this number 3 is it's important to know what's going on behind the scenes. What is the computer actually doing? So it's not just this mystery box making all these, amazing calculations that, whoa, how's it? And we don't know how it works. It's important to know how it works before we can use it properly. So with number 3, what's the difference between critical T and sample T? So when we do a problem by hand, right, and we're using our T formula, where we are taking a sample mean minus some theoretical population mean, and then dividing it by, let's say, the standard error to come up with our calculation. I really hope that that's that's the right formula because, like I said, I don't ever do this stuff by hand. I only know these formulas because I have to teach them to you. I know in my brain what it stands for. But so we do this calculation and we get some value, right? Let's say we get T equals, I don't know, 1.97. Okay, well, what does that tell me about my problem? What does that tell me about what I want to do? Am I going to choose the null hypothesis, or am I going to choose the alternative hypothesis based on that result? Just having this one calculated sample T, right? Because we'll get this based on whatever we plug in from our sample. That alone does not tell us what to do in terms of, do we accept or reject, or not accept? Do we reject or not reject that null hypothesis? That's the ultimate kind of question we want to answer here is, do I reject or not reject that null hypothesis? Having just the sample T doesn't allow us to make that decision. We need something to compare it to in order to make that decision. And that thing that we compare it to is the critical T, because the critical T sets our boundary for, okay, well, is this in or is this out, is essentially what we want to figure. Is this fair? Is this foul? If we're thinking in terms of sports analogies. So when you think of that baseball diamond, right? We've got the field. Pretend that this is pretty like like this. I am not an artist, as I've said before. But we've got these boundaries set, and these really are our foul lines, right? So our foul lines tell us, well, if it's inside the foul lines, this is considered fair, fair play, keep playing, we're all good. If it comes outside of these foul lines, then it's considered foul, right? And we have to do something else, right? It doesn't count, or something else happens based on whether it's in or it's out of these foul lines that are set. Now, when you think about foul lines in sports, do we set the foul lines differently for every game? No, that's silly. Like, the foul lines are set ahead of time. We don't come up with, well, what counts as foul every time, and every time it's a little different depending on what's going on. No, those foul lines are set ahead of time. We set them, they remain the same, and they are what we compare to make some sort of decision, in or out. The critical T works the same way. The critical T is set ahead of time, just like the foul lines are set ahead of time and they don't move. The thing that changes, that then we make some sort of decision based on is, okay, for example, in baseball, where's the ball? Is the ball in or is the ball out? And where the ball goes each time changes, right? The ball can, sometimes it's out, sometimes it's in. It can go all over the field. It can go every which way. Let's say it goes back here, right? It can go everywhere. And so that ball changes with each hit. The foul lines do not change with each hit. The foul lines remain the same. The foul lines are the boundary that is set ahead of time. And we look at that, where did the ball go? And we compare it to those boundaries and we say, okay, are we going to make the decision? Is it in or is it out? That's the same thing that we're doing with critical T versus sample T. We have this, and in T's, we're always talking about our sampling distribution of means, right? All these possibilities that we could see happen. Those foul lines, those get set ahead of time, right? So we would set, if we're using an alpha of 0.05, which we always are in this class, then that tells us, okay, my foul lines are going to be wherever there's 2.5% of my curve up here, and there's 2.5% of my curve down here. So if my ball falls somewhere in between, it's going to be considered fair. And that's when we're going to say, okay, that null hypothesis seems fair. I'm going to just stick with the null hypothesis if it lands in this kind of fair zone. However, if my sample T that I calculate ends up outside of these boundaries that got set ahead of time, then I'm going to call, in this case, no, foul. I don't think that null hypothesis is fair. I call foul on that, and it's out. The null hypothesis is out in that case, right? So these boundaries that get set, and these boundaries in our t-test are based on a couple of things. They're based on where they get established is based on, number one, what is our alpha value? Because that tells me what percent I'm using to set those boundaries. And it also depends on my sample size. So these are the things that help me set critical T. They set the boundaries. And so, but again, we'll know what that sample size is going in. We know what alpha is going in. So before we hit the ball, before we calculate sample T, we can set those and say if it's in this boundary, that null hypothesis is fair. If it's out of the boundary, the null hypothesis is foul and I'm going to reject it. Okay. So this gets set ahead of time. Sorry, I know this is getting really crowded. But this gets set ahead of time. This is like our baseball diamond, all set up, ready to play. And then we hit the ball. We hit the ball by calculating, okay, we have a real sample that we collect. And then based on the data that we get in that sample, we calculate the sample T, which in this case is going to be our, let's see if I can make it a little more realistic. This is going to be our baseball, right? So we take this sample T that we calculate, this is our baseball, and we say, okay, did this hit land in where the null hypothesis is fair, or did it land out? In this case, we would have some value that we set ahead of time based on our alpha and our sample size. And usually this is going to be, it's always going to be higher than 1.96 because that's where it kind of ends the cutoff point. But this could be, let's say this is 2.12 instead, right? Based on whatever it is, this is 2.12. Well, if that's 2.12 and negative 2.12, where is 1.97 in relation to that? Is it in the boundaries between negative 2.12 and positive 2.12? Or is it outside of those boundaries? Well, 1.97, if we were to plot it, it's not going to be higher than 2.112, right? It's going to be probably somewhere around here, 1.97. So based on where our sample T baseball got hit, in this case, where is it landing? Is the null hypothesis, are we going to conclude it's fair or it's foul? Since it's in the inside boundary, we would conclude it's fair. We would not be able to reject this null hypothesis. Now let's say that instead of this sample T we got, I'm just going to change this part. Let's say we got 3.97. Where would 3.97 land? Well, 3.97 is going to be past the 2, past a 3, almost to a 4. It's going to be landing somewhere way out here. This is where, oops, 4, I didn't mean that, 3.97. Well, if we hit way out here at 3.97, this is definitely going to be in our foul zone. And in this case, we would say, nope, not fair. We are going to reject the no in favor of the alternative. Same thing if we got a negative 3.997, right? That would be way out here in this land. So it doesn't matter if it's on this side or this side in baseball. Either way, it's foul, right? Same thing with our T. The critical T sets the boundary ahead of time. The sample T is like our baseball. Okay, where did it get hit this time? Is it in and it's fair, or is it out and we reject? So hopefully that helps to make this make a little more sense. And like I said, this critical T sample T comparison, we do this when we're working a problem by hand. And the critical T we get by either looking it up in a table And again, the table will be set up so it has like different alpha levels at the top. Put this down a little bit. It'll be set up so it has different alpha. Come on. Go down a little bit more, I guess. Here we go. It'll have different alpha levels at the top, like 0.05, which is what we use, or sometimes it'll have columns for like 0.01 or 0.001. You might see a column for 0.10, but it'll have different columns that say, well, which alpha are you using? In this class, we're always using 0.05. And it would have a column with n values. What is your sample size? Is it 2, 3, 4, 30, and so on? So you would find the column that has R alpha, and you would find the row that has the appropriate sample size, and you would look at the value. Let's say the sample size, we're a really small sample and it's 4. You would look at whatever value is listed in the table right here. Let's say it's our 2.12. I think it's probably going to be a lot higher than that in this case, but just to match our example. So we would say, oh, 2.12. Okay, then this is where I have to set my boundary. This is my, let's go back to our blue for it. This is my critical T. That's what I'm going to put right down here to set my boundary, to set my fair versus foul boundary. Okay, so if you're doing it by hand, you either need to use a table of critical T values like this, or as we'll see in our confidence interval work through, there are websites where you can just type in what is your alpha, what is your n, and it will tell you that number. You don't have to look it up in a table. That's really the old school method. Okay. But if you look at a statistics textbook, if you flip to the very back, you're going to see big tables like this with lots and lots of numbers that have all the different critical T's listed out that you would use. But again, that's the old school method. We're going to update it, and we're going to go to a website where you just type in your values and it says, blah, this is your critical T that you want to use to set your boundary. Okay. So that is critical T versus sample T. How about what we really do in practice, alpha versus p-value? Well, I'm not going to do the whole baseball diamond again. Hopefully you got that part. So in using a computer, behind the scenes, the computer is doing all this work, right? It's doing it by hand, if computers had little computer hands working. What we end up seeing when the computer does all its computery magic behind the scenes is we end up seeing blah, 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 it spits it out. It spits out T equals, I'm going back to my original one. Computer says T equals 1.97. Okay, but it will also tell us something like P equals 0.061. The computer will give us a p-value. When we're doing it using the computer, this is really where we want to focus. The p-value becomes more important for us when we're using the computer versus all this T versus T. So we're just going to extend this analogy. So we got our SDOM here. We're still going to have, some imaginary boundaries set just for consistency's sake. Let's set our boundaries. The boundaries are set ahead of time. And these boundaries, again, they're still based on these two things, alpha and sample size. But the computer knows what your sample size is because we put in the data and it could say, oh, I see you have 20 pieces of data. That means your sample size is 20. What the computer needs to know is, what alpha level are we using? Because that, again, is going to set these boundaries. So we tell the computer, I'm using an alpha of 0.05. And a lot of the time, these computer systems like JASP, they're set to use this alpha equals 0.05 by default. So we don't even necessarily have to put that in. It's assuming you're using 0.05, right? And if you're not, you got to tell me otherwise so I can make adjustments. It will assume that we're using that 0.05 based on the data we put in. It knows what n we're using because computer can count how many data points we have. So the computer will automatically come up with these boundaries, and we don't even need to know what number represents that boundary, because that, at this point, that's all the computer's business. We don't care. Computer will find out, okay, well, based on this and based on everything, I can tell you remember when we're talking about this curve, we're talking about the area under the curve representing probabilities, right? And so the computer will say, okay, where did your baseball land? It will calculate your sample t, and then it will say, okay, where did this sample t land? This sample t landed at 1.97, right? Just like up here. So 1.97, this is our, again, theoretical baseball. Where did it hit? And then what the computer does is it says, okay, so based on where that landed, this is the probability associated with landing there or higher. So this p-value it's giving us is telling us the probability associated with where our specific baseball landed, where our specific sample t landed on our curve. So it's being even more specific than saying in or out. It's saying here's the total probability of what you're seeing happen. So then based on that probability, we need to make the decision, okay, well, does that mean fair or foul? Are we going to keep the null hypothesis, or are we going to reject it and go with the alternative? This, again, is still the question that we want to answer. If we saw it all drawn out like this, of course, we can see in the drawing, in versus out. But the computer doesn't give us this drawing. The computer gives us, here's your t and here's your p. You make the decision. So how do we make that decision with just this information if we don't have a critical t to compare to? That's where our alpha really comes in. So again, alpha is set ahead of time. That's our boundary, right? So our alpha represents where our foul line is. So we have an alpha value, and it, like I said, in this class, in most cases, we're going to be always using this 0.05. And so this is the set boundary that we start with. Then the computer says this is the p-value. Okay, so we've got a p-value. The alpha is our foul lines, right? This tells us in or out. And then the p-value, this is our baseball. Where did our p-value, what p-value did we get based on where we hit based on our sample? So in this case, our p-value is 0.061. So instead of comparing like 1.97 versus 2.12, we're comparing our p versus our alpha. The alpha we know sets those boundaries. The P tells us, are we in or are we out? So the way we do this is so we want, let me think of the best way to say this. And I'm going to go ahead and clear some space just so we can, let me go ahead and clear. Hopefully you saw all of this okay. So we want to compare our alpha versus our P. So if P is less than alpha, then that means we're in our foul areas. Then this would be foul, and we would reject the null hypothesis. If P is bigger than alpha, and again, think of this little Pac-Man dude. Which way is it eating the thing that's bigger? Right? So here's my Pac-Man eating what's bigger. I swear I learned that in like 5th grade or something, and it still works for me. So if our p-value is bigger than our alpha value, then that means it's in the fair region, and we do not reject our null hypothesis. And I will tell you, I have seen the equals on this one. I have seen the equals on this one. The equals is a weird one. I'm going to say, like, I'm not super picky. If it lands exactly at 0.05, I generally tend to say, then it, now I don't even remember what I tend to say. In our class, hopefully we don't actually ever end up with a 0.05, but that's one that you could sort of argue like one way or the other. It almost never happens where it's exactly 0.05. It's either going to be a little bit bigger or a little bit smaller. But so let's go ahead and say that if you want to be more strict, we would say, no, it has to be definitely less than 0.05. If you want to be less strict, then you would put that equals here and say, at least 0.05. In this case, so we'll say, let's look at our p-value and our alpha. Which one's bigger? Which one would Pac-Man want to eat? Because he wants a bigger meal. Pac-Man would want to eat this one because 0.05 is bigger than 0.061 is bigger than 0.05, right? If we were comparing 61 versus 5, that's actually not true. 0.061 versus 0.05. This one's bigger, right? 6 is bigger than 5. So since P is bigger in this case, we're looking at this version for this example. Since P is not smaller than alpha, we would say, nope, this is fair, do not reject, right? Which corresponds to what we see here, where it would actually land inside. So we want to keep in mind this. If P is smaller than alpha, we reject the null. If P is bigger than alpha, we don't reject it. And so to help us again remember this, we go with Snoop Dogg. That's kind of hard to read, isn't it? If the P is low, the hoe must go. Right? If our P is lower than our alpha, we reject the null hypothesis. So remember that little mnemonic. If the P is low, if the P is lower than alpha, The home must go. Reject the null. And as usual, my short explanation was not so short, but hopefully this is making a little more sense. Okay. So remember, in this class and in practice, this is what we're going to be doing. We're going to be always comparing. We have some alpha, almost always set to 0.05. The computer gives us a p-value based on our sample, and then we compare those two. If the p is lower, reject the null. If the p is not lower, we don't reject the null. Now, back up here to 1 and 2. I will try to make these ones faster so we can get to the real, what you want to see with the confidence interval stuff. Okay, so you may have heard of one versus two-tailed hypotheses tests. If you need clarification on what the difference is there, watch this video, right? That's included in the classwork. So down here, we're assuming we're using that there's foul lines on both sides, right? That's sort of like if same thing. So when we're talking about one versus two-tailed hypotheses, we're basically talking about, do we have one versus two foul lines, right? Do we have a foul line on both sides of our curve or just one side of our curve? With a one-tailed test, we would be putting our whole 5% on only one side. It's like having a baseball diamond where only if it's on this side is it foul, but everything else counts as fair. It could be way over here and that would still count as fair in this version of baseball. There's only a right hand foul line, right? It could land in the, it could go way up behind and hit somebody in the crowd and it would still be considered fair if we were using this version, if we were using a one-tailed version, right? We could get a baseball landing way over here and it would still say, that's fair. That's okay. Alternatively, we could have a one-tailed where we set that foul line on the left-hand side and we say, okay, all of my 5% is over here. Doesn't matter where, it could land way out here and it would still be considered fair in this case. As long as it's not, on that left-hand foul line, then it's fine. So that seems a little silly, doesn't it? So this represents our one-tailed, where we're putting all of our fouls in just one of our tails, either on the right or on the left. And anything else counts as fair. Versus two-tailed is like what we talked about, where we say, okay, well, half of that 5%, so 2.5% will be here, and half of it will be here. And it doesn't matter if it's foul to the left or foul to the right, either way is still a foul, right? If it lands out here, it's foul. If it lands out here, it's foul. In this class, we will always, always be doing two-tailed. We don't do one-tailed. And the reason for that is because we could miss something really interesting if we're doing a one-tailed. We want to see, the reason we do this testing is because we have some question that we don't know the answer to, and we want to figure out what's going on, right? If we do a one-tailed, we're completely ignoring one side of what could happen. And I don't like that. And most researchers don't like that either. So just a little kind of analogy or story for you. So let's say we have a researcher who is an instructor, right? They're a teacher and they want to they have this great idea. They know that this teacher, this instructor, is all about the show Grey's Anatomy. And they know that a bunch of the students in their class are all about that show Grey's Anatomy too. Because every week they come in and I mean, and they talk about, oh, did you see Grey's Anatomy? What about, you know, McDreamy and McSteamy and all of that nonsense? I haven't watched for a long time. So this instructor is convinced that because their students are so into this show, that if she makes her test items using those characters, that the students are going to do better because they're going to be like, oh yeah, they're going to relate to it more. And so she makes one version of a test where all the word problems are with people who are nobodies, made up characters. So we have the non Grey's Anatomy test. And then she makes a version of the test where all of the word problems are using characters from Grey's Anatomy. And she thinks this will make it more relatable for my students. They'll be able to visualize it better because they can think of these characters that they know. And she's convinced that performance on this test is going to be better than the performance on this test. She's so convinced that she does a one-tailed test where if the difference lands somewhere up here, that means she's right. That the Grey's Anatomy, using Grey's Anatomy characters in her tests and in her teaching is going to improve student performance. She's so convinced. She says, I don't even need that other tail because they're definitely going to do better with this. However, right? When the scores come in, the students were so sort of distracted by thinking about what the characters in the show would do that they paid less attention to what was actually in the word problem, and they actually perform a lot lower than the people who didn't have that distraction, right? The people who were just focused on the word problem and didn't think, well, if it really was, Meredith Grey, or if it was, gosh, it's been a while, whoever, right? So they actually perform way lower on the GA test. How that would look when she runs the numbers is she would get some value way down here. But according to this one-tailed test, that's fine. There's nothing going on. The null hypothesis, that it doesn't look weird at all. She would be missing the fact that no, it actually makes their performance significantly lower because she was so convinced that it would be higher in the first place, right? So it keeps you from seeing something that might go in the opposite direction of what you anticipate. Okay. And so that's why we don't do one-tailed tests in this class. I don't like to assume one way or the other. I may think it's going to make their grades better, but I'm not sure. That's why I have to do the research. It could, in fact, make their grades a lot worse. And wouldn't you want to know that? Wouldn't you want to know if it's actually hurting your students and not helping them like you think they would? So this is why we do two-tailed, because this will flag it either way. It will flag it if they do way better. It will flag it if they do way worse. And so you'll know either way. Here, this would not get flagged, and she would conclude, there's no difference between them. When really there is a difference. The difference is they're doing worse, right? So we don't want to miss effects that we don't anticipate, right? And so this is why we don't do one-tailed tests. And this is why most researchers don't do one-tailed tests. You're basically front-loading what you think is going to happen, which can bias your results in a certain way, when you think about it. So In all of the t-tests that we conduct in this class, you should assume that they are two-tailed. We are not going to put all of our eggs in one basket. We are going to let the data speak for itself. And if it goes the way we think it is going to go, cool. If it goes the opposite way, great. I want to know that too. And if it's somewhere in between, good. You know, I'm still getting an answer. So that is our page 1 review. Let's see, how long did that actually end up taking? A really long time. Oh my goodness, 45 minutes. Sorry, guys. I wanted that to be like a 5, maybe 10-minute recap, but the number one thing I have learned from teaching is that everything takes me longer than I think it will. Okay, so let me go ahead and try to get rid of this. Square is. Nope. Okay, I'll be right back. Okay, so what we really want to see, I will put a disclaimer up when I put the video up saying, if you want the review for page 1 stuff, watch the whole thing. If you don't, skip to minute 46. Okay. So, challenge, solving the mystery of the mean. So, hopefully all of that explanation we just did makes this part a little easier to understand. So, to illustrate this concept of confidence interval, we're going to use this little scenario, this little made-up scenario that we came up with, where let's say we have a population, and it's a really small population. There's only 100 people. We take this 100 people, and we're interested in stress levels among this group. We want to know, how stressed is this population? So, since it's a small population, we're actually able to collect data from everybody. Isn't that cool? Sorry if you just heard a weird noise, that's me drinking water. So, in this population, I have taken the time and measured every single person's stress score. So I know exactly what the mean stress score for the whole population is and what the standard deviation for the whole population is. But I'm not going to tell you because I'm trying to simulate how research works in the real world, right? So the population mean stress score is a mystery, and I want you to try to figure it out based on just a sample, because that's really what we're doing in stats and research, right? That simulates what we're doing in the real world. So I'm not going to tell you what the mean stress score is. I'm not going to tell you what the standard deviation of the population is. Those are a mystery. What I can tell you is that the shape of this population is normal. And so thanks to that, and thanks to the central limit theorem, that means that we know that the SDOM is also normal, right? That's why I have that little hint there, is we know nothing funky is going on with the SDOM. You can assume it's normal, just as we usually do. Now, as a class, I want you to try to solve the mystery of the mean. I want you to try to figure out, based on just a sample, and then based on looking at what everyone else's sample says, can you figure out what the mean, the real true mean of the population is, right? So we are trying to figure out, what is that true population mean? That's the mystery. So it's your job to try to narrow down the suspects and come up with the best estimate you can for what that average stress score of the population is. And again, you can work together with a partner if you like on this. Now, we're going to be using a couple websites to help us here. I want to make this. This is always the problem when I'm in tablet mode, is I don't have a mouse. So it's hard for me to get things to look exactly as I want. Okay, that'll work. So we're going to be using a couple of websites to help us. So the first thing you want to do is go to this website, and this website is set up where I put in all the potential population values, and this website is going to choose a random sample of 10 stress scores from our population for you. So you don't have to worry about, am I being random, about choosing the random. This website does it for you. So hopefully this works out. Oop. How do I think I need this guy. I can't hold control when I'm in tablet mode. How do I do this? I'm gonna do there. Hopefully this works. There we go. This is everything is a learning curve for me, just like it is for you. Okay, so this website will open up, and right here on the right hand side where it says picked, this right here, these 10 numbers, this is the random sample it just picked for me. So let me set this up so I can hopefully see. Ay, Dios mío, eh? I want to be able to see those picked numbers at the same time. I don't want the one on the left. There we go. Okay, so I can see those picked numbers and be able to write on my classwork at the same time. So your 10 scores will be in the right-hand box labeled picked. Write down my 10 scores here. So I got 22, 17, 11, 12, 10, 18, 14, 8, and 13. That's my random sample of 10 scores. Let me make sure there's 10. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I missed something somewhere. 1, 2, 3, 4, 5, 6, 7, 8. Why do I only have 9? What's going on? Did I miss one? I'm going to reload this because I should have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Somehow I dropped one. So let me do this again. I could edit this all out and let you think that I do everything perfectly the first time. But this way you can see I F up just as much as every other person does, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Whatever I messed up last time, I didn't mess up this time. Here are my 10 scores for my random sample. Okay, so now I'm done with this website. I don't need this website anymore because I have my 10 scores picked. So the next thing I want to do is calculate the mean and the standard deviation of my sample. So the mean, and remember, since this is a sample, right? This is not the whole population. This is just a sample from it. That means I'm using this symbol, X bar, sample mean. I need to figure out what that is, and I want to figure out what the sample standard deviation. And actually, here, I'm not just figuring out the sample standard deviation. I want to figure out that estimate for the whole population based on this sample. So I'm using this S symbol, right? But again, they're both based on a sample. So just to review, The formula for finding a sample mean is to add up all of our sample values and divide by the number of items in our sample, right? So in this case, it would be adding up all 10 of these values and then dividing by 10 because we have 10 values. So I could do that by hand, 16 plus 16 plus 11 plus 24, blah, 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 blah. But again, I might make a mistake. So I'm going to use a calculator to help me. Just to review this formula, the estimate for the standard deviation based on a sample, this is that sum of all the deviations squared divided by n minus 1, and this n minus 1 is because we're doing that estimating because we know we got to fudge those, excuse me, we got to fudge those numbers a little bit. So again, we could do this by hand, but that would be messy and take a long time, and I would probably make a mistake because I make a lot of mistakes. So instead, we're going to use this online calculator. To do it for me. And then I can feel confident that I didn't screw it up. Okay, so these numbers, it starts with some numbers in here that these are just, I don't know, the numbers that it throws in. These are not my numbers, right? So I need to edit these so that these are my numbers. So let me, oh, I miss having I need a backspace button. I've got this crazy, sorry, go back the other way. I've got this Surface book that I got when I started teaching because it lets me detach and switch to using just the tablet. But it can be a major pain in the butt sometimes trying to figure out how to work it. Here we go. Let's switch to, okay. I've had this thing for like almost 3 years. You'd think I'd be better at it by now, but I'm not. Okay, so my numbers that I'm going to put in, just move this so I can actually see them, are 16, and it says separated by comma. So 16, 16, 11. Oh, that didn't. 11. 11. Oh, this is so annoying. Okay, let's try this way. 16, comma, where's comma? Okay, this part I'm probably going to edit out because this is ridiculous. Comma, 16, comma, 11, comma, 24, comma, remove this so I can see, 18, comma, 7, comma, 15, comma, 7, comma, 4, comma, 10. Let me check. 16, 16, 11, 24, 18, 7, 15, 7, 4, 10. That looks right. And remember that your 10 scores are a sample, right? This is the sample. This is not a population, it is a sample. So you have to make sure you select this sample button here. And now I want it to calculate for me. And the cool thing about this online calculator is, okay, it verifies my sample size is 10. If I were to add up those 10 values, it would be 128. The mean is 12.8. Let me write that down. 12.8. And the standard and the variance, if I wanted that variance, and then it shows me, oh, working out all this blah, 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 just like we did in that classwork like 3 or 4, I can't remember exactly. But S, as you remember, is the square root of that variance. So S here, 6.088. And I'm just going to go ahead and round that up. Instead of 6.088, I'm going to round up this 8 to a 9. So 6.09. And that's about as precise as I need to be for this. All right. So I now have my sample mean and my sample standard deviation. Yours will obviously be different because your sample is probably different. Okay, but this is what I got, and you can see how I did that. Now, am I 100% confident that the mean of my sample, which is 12.8, is exactly the same as the mean of the whole population? No, I am not. I am not confident of that because this is just 10 values out of 100 values. It might be 12.9. It might, wait, did I say I was going to? No, yeah, okay. It might be 12.9. It might be 13.1. It might be, oh, this is very annoying. It might be 12.5. It might be 11.8. It might be something near 12.8, but it's probably I'm not 100% confident that it's exactly 12.8, right? It could be a little different, and probably is a little bit different. Now consider, what seems like a better way to estimate the mean of the population? To say it's exactly the same as this mean of my sample, or to say, well, I'm pretty sure it's in this range of numbers around my sample. It's probably, I mean, based on this, I don't think it's likely that the mean of the population is 75. That seems ridiculously far away. I don't think the mean of the population is 2 because that's pretty far away. But I would, I might feel pretty confident. If you ask me, if I win $100, if I get it right, I would say maybe I would guess somewhere between like 11.5 and 13.5, right? I want to give myself a little cushion room to give myself a better chance of getting it in there. So would I rather say it's exactly 12.8, or would I rather say I'm pretty sure it's between this number and this number? I'm going to choose that pretty sure between this number and this number. And if you want another illustration of why, go ahead and watch this YouTube video of The Price is Right. I forget the name of this game. Anyway, whatever range game. It says it right here. The range game. This kind of illustrates the idea roughly of what we're doing with confidence intervals. We're saying, I'm pretty sure it's between this number and this number, rather than saying it is definitely this one number. Okay, so I would rather do the range because that increases my chances of being right. So we're going to go with that second option from number 7 by calculating what we call the 95% confidence interval based on the information I got from my sample. Now there are 2 formulas that we've reviewed for calculating confidence intervals. This one on the left and this one on the right. And we need to figure out which formula should we be using today. Well, in this case, what is the difference here? The difference is, are we talking about Z and sigma? Or are we talking about T and S? So remember, sigma is the population standard deviation. Did I tell you what that was? No, I specifically did not tell you what that was, right? It's a mystery. So that means we don't have sigma. And since we don't have sigma, we can't use z. So we're not using this one. What we do have, thanks to that online calculator, is we have S. We have that estimate based on our sample. So in this case, we will be using this one. It's going to be based on a t curve instead. So which formula should we use today? This one. Why? We don't know sigma, only S. Now, I'd like you to rewrite out or copy over the appropriate formula below, and then we're going to label what each of these things stands for. So, CI equals X bar plus M minus parentheses T times S divided by square root of N. Now again, whole bunch of symbols. What do they mean? Okay, so let's just switch to a different color for labeling. So this is my confidence interval, right? This is what we want to get at the end of this. So we could say, I'm pretty confident that the population mean is between this number and this number. This X bar, this is our sample mean, right? That's what this symbol stands for. This is going to say, this means add and subtract. And this is how we're going to get two different numbers, because we're going to get one number by adding and one number by subtracting. So those two numbers are going to be the between this number and this number. That's how we get two numbers here. The t, well, in this case, the t that we're going to need to get is the critical t. That's what we need to plug in there, right? And we're going to use one of those websites, like I mentioned, to find out what that value is that we need to plug in here. Critical t based on our alpha and our sample size. This S stands for our standard deviation estimate based on our sample. You don't have to be this specific on yours, but I want to be more specific so you can see what I mean. So this is the standard deviation that we got based on the sample. And this N, what does that N stand for? That stands for how big is our sample? What is our sample size? Right? And then this is multiply, this is take the square root. We don't need to label all those. Okay, so we just need to figure out what are all the different components that we're going to plug in for these, missing values so that we can solve to get our confidence interval. So let's identify those numbers that we need to plug in. So what is our sample mean? So our sample mean we can find in number 6. My sample mean was 12.8. So that 12.8 is what's going to be plugged in right here in my equation. Now, what is the population standard deviation? Do we even know that? Well, population standard deviation is sigma, and we don't know it. So what can we use in place of sigma when we don't have it? We're going to use S, that estimate for it based on our sample. So we're going to use S, and in this case, our S, again, we calculated in number 6, is 6.09, at least for my sample. Yours, again, should be different because your sample is probably different from mine. So it's okay if your numbers here and here don't match mine. That's okay. Now, what is our sample size? What is our sample size? Well, how many numbers did we choose for our sample in the first place? 10. So now we know what numbers are going to be plugged in here, here, and here. This is going to be my 12.8. This is going to be my 6.09, and this is going to be 10. And your values that you identify are going to be the ones that you plug in. So we're still missing one value that we need in order to calculate, and that's this critical T. So since we want to calculate a 95% confidence interval, because we can choose different values there. We could say, I'm okay with being a little less confident, only 90% confident. Or maybe you say, no, I want to be very confident. I want to be 99% confident, right? So we can choose that confidence interval, but most of the time we use 95%. That's pretty standard. And that's standard because of alpha equals 0.05. That alpha is the other 5%, where our 95% plus our 5% from alpha, that adds up to our 100%. Okay? So it depends on what our alpha is. In this case, we want to be able to say that we are, and this is important, you may or may not see this on an upcoming test. So what does that confidence interval actually mean? It means we are 95% confident the population mean, that mystery we're trying to solve, is within the interval we calculated. That's what this confidence interval is telling us. We're pretty sure, we're 95% sure that the real true population mean is going to be within these two numbers that we're calculating. And that's what this formula does. So since we're using the formula above that has T in it, right? Since we don't know sigma, then we have to include a critical T value in the formula. This critical T value represents the place on a T distribution that cuts off, that sets those boundary points, that cuts off this middle 95% from our outside 5%, right? 2.5 plus 2.5 is 5. So hopefully that earlier description, I hate when it does that, oh well, helps clarify, right? We are trying to identify what number right here is going to cut off this middle 95% from the outside 5%. That's what we need to plug in here, is what is this T value? So we need to find the T value that goes with these cutoff points for our middle 95% area. And since there are lots of different T distributions, as we talked about, there's, fatter ones and taller ones, they all are a little bit different. Then the T that we need is going to depend on our sample size. So we could look up the critical T value using one of those critical T tables, but that's a pain in the butt and it's hard to do. It's confusing. So instead, we're going to use computers and we're going to use an online simulator instead. So to get to this simulator, you can click on this or type it into your web browser. Okay, and this is what this online simulator looks like. You see, so here it's not set up how we need it yet. We need to adjust it. We need to tell it what do we want to be that center probability. So that's going to be that 95% in our 95% confidence interval. So the central probability, I want that to be 95%. So I'm going to adjust this to be 0.95. Oh. And you see what I mean? You can set this confidence interval for whatever you want, and it's just really hard for me to do this precisely with my little stylus pen. Okay. You can also just type it in. That's probably a lot easier. 0.95. So now we have 95% in the middle, and it looks like this, right? So we also need to adjust the degrees of freedom because that n is what is also going to help us determine what that cutoff point is. Right now, it's saying that n equals 51. We don't have a sample size of 51. We have a sample size of 10. So we need to adjust this so that this degrees of freedom is equal to n minus 1. Now remember that n is our sample size. So in this case, we're going to set this bottom one to be 10 minus 1, or n minus 1. So what is 10 minus 1? Hopefully that's an easy answer for everybody. Let me just try to do it this way first. Boom. 10 minus 1 is 9. Okay, and you see how based on our different n values, this curve ends up looking a little different when it's really low. You see how it changes the shape of that curve? So it's got these fat tails and it's shorter. That's what's happening based on our sample size. It's telling us which specific t curve to look at. In this case, we want the t curve that corresponds to sample size of 10, or 9 degrees of freedom. So now I can see I've set it to be 95%. I've set it to be n minus 1. What is the critical t-score that it gives you? So you want to look right here, this t-score right here. This is what we want to plug into our equation. So in this case, my t is equal to 2.2621. And I'm just going to drop, just for simplicity's sake, I'm just going to drop that very last 0.0001 because we don't need to be that precise. Okay. So this is the t I'm going to be using. T equals 2.262. So now we have all of the pieces that we need. So here's our formula again. To get our confidence interval, we need to plug in the different values. So just so I have it again, I want my sample mean. I'm going to do it twice, the first time adding, the second time subtracting. And then I'm going to plug in that t that I just got, that critical t, and multiply it by my s divided by square root of n. And I have this little hint here that it's easiest to start out by figuring out what is this first, then multiply by this, and then do this part. So we're going to do first part, second part, third part, okay, in steps. So the first part, let's figure out what is my s divided by square root of n. And let me go ahead and just plug in all my pieces so I can see this written out all together. And again, this is a 95% confidence interval. So, wish I didn't have to scroll so much, 12.8 plus and minus the t, 2.262, multiplied by my s was, I think, 6.09. Is that right? Yep, 6.09. Divided by the square root of 10. Okay. So I want to figure out this piece first. So what is 6.09 divided by the square root of 10? Well, let's just use a calculator to help us with this. So 6.09 divided by, and then you got to kind of do this little piece backwards. It's 10, but not just 10, we want the square root. So on my calculator, it has a little 2 square root. This is the one we want. So we can see it said 6.09 divided by the square root of 10 is 3.16. I'm just going to go to 2 decimal places. So 3.16. So that means this piece right here is 3.16. Now, that's step 1. We need to do step 2, where we multiply the t by this 3.16. So instead of, clearing this out and doing it, I'm just going to say, okay, so this 3.16 that I just got multiplied by, oh, I don't know why it just changed that. Okay, so I guess I will clear it out. Okay, 3.16 multiplied by 2.262. Because it doesn't matter if I put this number or this number in first. 2.262 times 3.16 is the same as 3.16 times 2.262. So this is telling me this whole piece right here is equal to 7.15. Again, I'm going to round that to 2 decimal places. So 7.15. And again, it doesn't matter which direction you put this in. 2.262 times 3.16, 7.15 rounded. Okay, so that is step 2 done. Now step 3 is where we're going to take this 12.8 and first we're going to add our 7.15, and then we're going to do it again to do 12.8 minus 7.15. So let me kind of write that over here. So 12.8 plus 7.15. This is going to give me one of the numbers for my confidence interval. And then I'm also going to do the same thing, 12.8 minus 7.15. So let's figure out what those are. So in this case, it does matter which number we put in first, because adding and subtracting, it matters which one's bigger, which one's smaller, right? So 12.8 plus 7.15, 1995. So I got 1995, and then 12 point, shh, 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 shh. Hold on, got a barking dog right behind me. Go outside. Okay, 12.8 minus 7.15. You know what, I'm realizing I think I messed up somewhere. I think I messed up here. Let me just check something. What happens if I do this? Okay, I did mess up. So I did want that 1 point. I was thinking this is a really big interval. Let me backtrack. Let's backtrack. This is not 3.16. That 3.16 is just this. So let me backtrack. This number is going to be different. This value is different. Sorry, y'all. Let's try this again. Like I said, I mess up a lot. But thankfully, because of all my experience, I'm better at seeing when I mess up than you probably are. So this 3.16, this was just that bottom part. So we really do need to do, it really is going to be that whatever it came up with, that 1 point something. So divided by 10 square root. That's just saying what the 10 square root is. We need to hit the equal sign to get it. So that's my bad. This is actually 1.93. I'm going to round up that to 1.93. That's really this whole thing. Okay, so this piece is 1.93, which means that we need to take that 1.93 and multiply that by 2.262, and this is going to be 4.36. I'm going to round that up, 4.36. Right, so this whole thing, 1.93 times 2.262 is equal to 4.36. So that's actually what we're adding and subtracting. I was thinking that interval looks really big, a lot bigger than I would expect it to be. And again, that just comes from years and years of experience. Even with years and years of experience, you can see I mess up a lot. So don't feel bad if you mess up a lot too. It happens to all of us. Okay, so now let's try this again. So 12.8 plus 4.36 equals 17.16. And so that's going to be the higher part of my confidence interval. The lower part is 12.8 minus 4.36, 8.44. So these two numbers, those are my answer. Those make up my 95% confidence interval. So let's just make a different color so we can see it's the answer. So my 95% confidence interval is from 8.44, right? Because it's an interval. It's saying between 8.44 to 17.16, meaning I'm 95% confident that the true population mean is somewhere in this interval. Now, this looks a little confusing to say from this to this because it looks like I want to subtract it, right? So this is not how we usually write out the answer. So based on our sample, my confidence interval, we're going to use this format because, like I said, this looks like we want to subtract. We don't want to subtract. These two numbers are they're both our answer. So we would say 95% confidence interval is equal to my lower number with a square bracket, 8.44, comma, and then put the higher number, 17.16, and then close my square bracket. So this is how we would write our answer. For what is my confidence interval? I'm 95% confident that the true population mean, that mystery we're trying to solve, falls somewhere between the values of 8.44 and 17.16. Again, my sample mean was 12.8, but I'm not confident that that's exactly the same as that population mean. I'm pretty confident it's going to be somewhere between these two numbers, is what this means. So, what is an interpretation of this confidence interval? I am 95% confident the true population mean that we were trying to figure out is between 8.44 and 17.16. So at this point is when I want you to go to that discussion board, that extra discussion board. It's optional. If you don't want to do it, that's okay. But it will help everyone come to a better conclusion. We could see, okay, this was my confidence interval, but what did everybody else get? And by looking at what everybody else got and where they overlap, that can help us be even more precise, right? So we can think of our confidence interval like this was my sample mean was 12.8, but I'm pretty sure that true population mean is going to be somewhere between this lower value and this upper value. So based on what I know, what is my best guess for the true mean of the whole population? And I can be as specific as I want. I'm thinking I'm just going to go closer to my mean, but I mean, I could pick a lot of different numbers in here. I'm going to say 13.1. I don't know. Again, this is up to you. You can pick whatever number you want. That's just what popped out to me. Okay? So, hopefully that helps clarify what this confidence interval thing is. Why do we use it? And don't worry, we're not going to be doing these by hand. This was just to illustrate how does it work and what are all the little pieces that go into that formula that the computer is using. Thankfully, with computers, when we run our analyses in JASP, we can click a little box and it will say not only is our t-value this and our p-value is this, it's going to tell us our 95% confidence interval is this, and it's going to be those two values, right? A low number and a high number. So we don't have to do this by hand because, as you can see, as I beautifully illustrated on accident, it's super easy to make mistakes when you do things by hand. So we're not going to have to do that. The computer does it for us. But this, hopefully seeing it written out and doing all the steps helps us to understand a little better. What is this when when the computer, spits it out at us, what does that mean? Or how did it get to those numbers? This is how it got to those numbers. So that's my very long-winded, as usual, review of confidence intervals. So I hope that clarifies things, and I'll see y'all soon.